In this lesson, we're going to finish state standard number 2, and we're going to learn to solve systems of three linear equations. Again, this case we are not using matrices, we're using a new method, but you recall we did learn Cramer's rule, which was another method. This method is going to be called Gaussian Elimination. But first, before we get to the idea of how to solve it, our answer, if there is one, could be an ordered triple in space. So we can have an x value, a y value, and a z value. And that would be the solution to an equation that has three variables. So for example, the ordered triple 2, -4, +3 is a solution to this equation, because if we substitute in 2 for x, -4 for y, and 3 for z, that gives us a true statement. Now, for three equations, three variables, of course, that solution would have to make all three of the equations true. But an ordered triple, remember, is going to be a three-dimensional space. It's going to be a point in that three-dimensional space. And in three-dimensional space, we use three axes. There's the x-axis, the y-axis, and the z-axis. And if we wanted to look at that point 2, -4, 3, just like we would in a two-dimensional plane, we would start at the origin. The x-axis goes forward and back. So since it's a +2, we would come forward 2. The y value is -4, and the y-axis in 3D goes left and right. So we would go left 4 units. And then the z value goes up and down. The z-axis goes up and down. Z value is 3, so we would go up 3. That point, that little dot right there, would represent the point 2, -4, and 3. All right, let's take a look at another one, just so to make sure we have a good visual to go with what we're learning today. If we had the point 2, 3, and 4, again, we can represent that with a graph, and we start at the origin. We would move 2 units forward along the x-axis since it's a positive x value. Otherwise, we would go backwards on the x-axis if it were negative. And then since y is positive, we're going to go to the right 3. And then z is also positive. We're going to go up 4, and that would be that point in space, point 2, 3, 4. And we call an equation in this form ax plus by plus cz equals d, where a, b, c, d are real numbers, and they are all not 0. So not all of them are 0. We would call that a linear equation in three variables. But although we call it that, the graph of that line is not a line, but is a plane in space. And as we did with two equations, two variables, sometimes there is no solution. So what we're going to do is look at a couple of pictures of what could happen visually. That are three equations, each one representing a plane. They're all parallel to each other. There is no one common point to all three planes, so there would be no solution, and we would say that that is inconsistent. Another scenario is that you can see the blue and the yellow plane intersect. The green and the yellow plane intersect. The green and the blue plane intersect, but there is still not one point on all three planes. And then here's another possible situation. Two of the planes are parallel, and then they are cut by a plane as a transversal. So since there is no one point on all three planes, all three of those scenarios are a situation where we say there is no solution, and it is inconsistent. What does it look like when we have a consistent independent? When we get that one point, that ordered triple in space, that would come from something looking like this. We would have all three planes intersecting at one point. In this case, the pinkish-reddish plane, the blue plane, and the green plane all intersect at this one point, represented by the red dot. And that dot would be our ordered triple, as we talked about before, locating that point in space. So that would be consistent, because there is a solution. But since the solution is one point, an ordered triple, we would say it's independent. And then the last scenario is the consistent dependent that we talked about with two equations and two variables. And that occurs when all three planes intersect, forming a line. there's an infinite number of solutions, all the points that are on this line. So there is a solution. We would say it's consistent. It's one line, so we would say it is dependent. All right, so we're ready to, now that we've got that visual picture in our mind, to look at solving some equations. And this one is set up because most of the work is done, and it illustrates the goal of what we're looking for. Typically, though, all three equations will have all three variables. So we should have an x, y, and z in the second equation, an x, y, and z in the third equation. But this one illustrates what our goal is. Our goal is to try to get our system of three equations, three variables, to look like this, where the first row, or the first equation, has all three variables, x, y, and z. The second row only has two variables, y and z. And then the third equation only has one variable, z. And you see that it forms pretty much of a triangle. So that's our goal, a triangle with all three variables in the first equation, last two variables in the second equation, and then just the last variable by itself in that third equation. And so, as we said, this would be a scenario where most of the work is done for us. This is the goal. This is what we're trying to get. Once we get it to this point, we know that z is equal to 3. So now we want to find out what y is. And there's only one equation here that has both y and z, so we're going to use that. 2y plus z equals 1. We're going to substitute in our value of 3 for z. We're going to subtract 3 from both sides, divide both sides of that equation by 2, and then we will find out that y is equal to negative 1. Well, at this point, we know what z is, we know what y is, and we can substitute both of those values into this first equation to try to find out what x is. So let's do that substitution at this point now. Let's take that first equation, 2x plus 3y plus 2z equals 13. We're going to substitute in negative 1 for y, 3 for z, and we're going to find out what x is. So 3 times negative 1 is negative 3, 2 times 3 is 6. Negative 3 plus 6 is 3. Subtract 3 from both sides. 2x is 10. Therefore, x must be 5. So x was 5. Negative 1 represents our y value, and z value was 3. So we do have an ordered triple in space. We have a solution, so we say it's consistent. And then it is one point. We say it's independent. And that point represents this visual scenario where all three planes intersect at one point. So that's our solution to our first equation. And let's take a look at basically that triangular shape that we mentioned, which is our goal. We would like to get all three equations. First equation, all three variables. Second equation, last two variables. Last equation, just the last variable. That triangular shape, that goal, this process is called Gaussian Elimination, named after Carl Friedrich Gauss, who developed this method. All right, let's take a look at solving a particular equation. We've got x plus y minus 2z equals 7, negative x plus 4y plus 3z equals 2, 2x minus 3y plus 2z equals negative 2. What we want to do is we want to eliminate x twice. So here's my strategy. If we add the first equation to the second equation, you can see we have x and the opposite of x, and those x values will be eliminated. We're going to take that resulting equation, put it in the second row. So let's do that. Let's take that first equation, x plus y minus 2z equals 7. Let's take that second equation, the opposite of x plus 4y plus 3z equals 2. Let's add them together. X plus negative x drops out to 0. Y plus 4y is 5y. 3z minus 2z is 1z. And 7 plus 2 is 9. So what we're going to do is take my original system, keep that original first equation. For now, keep the original last equation. But the result we got from adding the first two equations together, we're going to put in the second equation spot. So far we do have the first equation with all three variables. we have the second equation with the two variables we want, y and z. So what we have to do now is we have to combine the first and the third equation to eliminate x again. And that will not be our triangular form yet, but we're getting close to it. So let's take a look at this process. To do that, we're going to take this first equation and multiply everything in it by -2. That will convert that equation into -2x minus 2y plus 4z equals -14. And if we add that to the third equation, the x's will be eliminated again. So our strategy so far was to eliminate the x variable twice. Add them, the x drops out. We have -5y plus 6z equals -16. And we're going to take that result and replace the last equation with that. And this is what it looks like. So now we have two equations with the same two variables y and z. And if we add these last two equations together, the y variable will drop out. We're left with z, which is our goal. So let's add. The y's will drop out and give us 0. Z plus 6z is 7z, and then 9 plus -16 is -7. Divide by 7. Well, we don't need to do that at this point yet, but we will. And put that in place of the last equation. So we have that triangular system. First equation has three variables. Second equation has the last two variables. Third equation has the last variable. And to solve this system, if 7z equals -7, then z must be -1. Let's take that value, substitute it into this second equation that has the two variables y and z. So 5y plus, instead of z, we'll replace it with -1. That is equal to 9. Simplify that and add 1 to both sides. 5y is 10, so therefore y is 2. Now that we know what z is and y is, we're going to take the first equation, replace y with 2, z with -1, and solve for x. So let's do that. Replace y with 2, z with -1. Simplify that. -2 times -1 is 2. That will give me 2 plus 2 is x plus 4 equals 7. Subtract 4 from both sides, and x equals 3. So if we put that together, we have an x value, which is 3, y value, which is 2, z value, which is -1. That's my ordered triple in space. There is a solution, so it's consistent. It's 1 point, and it's independent. All right, I'd like to do one other example. So let's take a look at this one and practice it again. We'd like to take the first equation. If we multiply everything in it by -2, add it to the second equation, the x will drop out. So let's do just that. Take the first equation, multiply everything through by -2. That'll become -2x plus 4y plus 2z equals +2. Add that to my second equation, just as it is. -2x plus +2x drops out. 4y minus y is 3y. 2z plus 1z is 3z. 2 plus 1 is 3. And we're going to take that result of combining the first two equations and replace the second equation with that. Because again, our goal is that the second equation contains only y and z. So now, what we would like to do is we would like to be able to take this first and third equation, combine them to drop out x again, so that the last equation will have y and z, and then we would eliminate the y. So we're going to do that by subtracting in this particular example. So let's take the first equation as is, x minus 2y minus z equals -1. Last equation as it is, x plus 4y plus 5z equals 5. Subtract them. So x minus x drops out. -2y minus 4y is -6y. -z minus 5z is -6z. -1 minus 5 is -6. And we'll place that in the third equation slot. because again, our goal in this triangular process, preliminary goal, is to get the second and the last equation to have only y and z. Right now, if we take the second equation, color-coded in blue, multiply everything by 2, you'll see that positive 6y and negative 6y will be eliminated. So let's multiply everything through by 2. Gives me 6y plus 6z equals 6. And when we add 6y plus negative 6y is 0, 6z plus negative 6z is 0, 6 plus negative 6 is 0. And we're thinking, wow, did we make a mistake? No. But let's just put that in the third position, just for the filler for a moment. And if you can recall way back to early on, we said that if you're solving an equation and all of the variables in that equation are eliminated, the thing to do is to determine if what's left is true or false. Now 0 equals 0 is obviously true. So since it's true, that means there's an infinite number of solutions. So what that means is that all three planes intersect at one line, and that every point on that line is a solution, and so we can say it's consistent dependent. So if I take a look back at our early examples, it's one of these scenarios where all three planes intersect at one line, when we got 0 equals 0 as the result of our last equation. Okay, and as you can see in this graph, all three of these planes are intersecting at this one line. So it is consistent dependent. Now, the one other thing, early in the school year, we said, well, what if you got a false statement? So let's just pretend that when we were combining those last two equations, instead of getting 0 equals 0, let's pretend that we got 0 equals 5. Which is a false statement. So if that occurs, that means there's no solution. And it's not possible at all for 0 and 5 to be the same. There's no solution, and our vocabulary word for that is inconsistent. And I'm just going to take a quick look at we don't know which possible scenario it is, but we know that there's no solution, so it could be that all three planes are parallel, or we have two parallel planes cut by a transversal plane, or that we have a situation like this where only two planes intersect with each other at any given moment. All right, so that's the last possible outcome. So what we have in that situation, again, if you're solving and all the variables drop out, check to see if it's true or false. If it is true, all three planes are intersecting at a line, meaning it's consistent dependent. If it's false, there's no solution, meaning it's inconsistent. And that's our last look at solving three equations, three variables, and state standard number 2.